Hi, this is Math 1050, and this video is over Chapter 6C. And for Chapter 6C, we're going to look at the normal distribution in more detail. So conditions for the normal distribution. The majority of the data will be clustered around the mean, which is also going to be very close to the mode and the median. They're all going to be very close together, and it's going to be the central point hump of the data. And so it has a single peak. Right. The data values will be spread evenly around the mean and have more of a symmetrical distribution. Large deviations from the mean will be rare, and you'll see kind of a tapering down for the tails on either side, on both sides. And so each of these data values are a result from a combination of many different factors. Okay, so on the right here we have a graph. It's a decent normal distribution. It's the chest circumference of Scottish military men. And you know, we see the hump kind of in the center here. This is going to be around where the mode, mean, and median fall. And then it tapers down in both directions. Now notice that it's not perfect. Okay, it's not a perfect bell shape. It's just you know, the bar to the left of the central bar is a bit higher, almost the same height as that central bar, and to the right it's a bit lower. You know, but they kind of go down somewhat the same on either side, and so it may not be ideal, but it's very close, and this is very good data for a real life situation. The ideal normal distribution would be a mean of 0, standard deviation of 1, where the standard deviation is on the x-axis. You'll have no outliers. Okay. It's okay to have a couple in real data, but with the ideal normal distribution, you won't have any. A single peak, and it'll be perfectly symmetrical. We really do not expect ideal normal distributions in real life. It's more of just how we're going to learn about this. And it follows the 68, 95, 99.7 rule. And what that means is, if you look at the mean, again, that's at 0, standard deviations on either side, -1 on the left side, +1 on the right side, that goes to 2 and to 3. From -1 standard deviation to +1 standard deviation should be 68% of the data. From -2 standard deviations to +2 standard deviations should be about 95% of the data. And then from -3 to 3, 99.7% of the data. Again, this is ideal. And we may not be exactly at that, but we should be close to it. And this is what we expect, not what we always get. This is what we expect to say we have a normal distribution. Right, now, I haven't mentioned the z-score much, but I've mentioned today a couple times when we talked about z-score. Z-scores and percentiles are two things that we use to look at the normal distribution. All right, so let's look at an example real quick. How much self-esteem do you have? All right, so if we will to look at a Rosenberg self-esteem scale, and suppose you scored 6.4 on that scale, do you have much self-esteem? Right. How can you answer that? Since you've never seen the scale, for any of these scores. Suppose I told you that your percentile rank in the sample of persons who've been given this scale is 80.6, or your 80.6 percentile. Now you know that you have quite a bit of self-esteem relative to others. What that 80% mean is you're 80.6% above everyone else. Or let me state it a different way. You're above 80.6% of all people. Which is quite a few people. Percentile ranks are an excellent way to presenting performance scores. We see this in ACT stats and SAT stats. They follow normal distribution, so you get a percentile, lets you know where you're at. If you're at 50%, you're right there at average. If you're above 50%, you're above the average. If you're in 70s or 80s, you're quite above the average. 90s for sure, you're really above the average. Right. So for percentiles, percentile of a data value is a percentage of all data values in a data set that are less than or equal to it. To that score. The z-score is the number of standard deviations the data value lies above or below the mean is called the standard score. Okay, to calculate the z-score, we take the data value, subtract the mean, and divide by the standard deviation. Right. If your data value is less than the mean, you'll end up with a negative. If your data value is the mean, you'll end up with 0. If your data value is above the mean, you'll end up with a positive value. Right, so let's look at IQ scores. Mean is 100, standard deviation is 15. So if you have a data value of 100, then your z-score is 0. If you have a data value of 85, then your z-score be negative. It would be a negative 15 over 15, which is a negative 1. And if you have a IQ score of 115, then your z-score is positive and is a positive 1. Okay. For each of these z-scores, we link a percentile to them based on the normal distribution, how it falls ideally. Right, and so we have a table where a z-score of 0, you have a percentile of 50%. A z-score of negative 1 has a percentile of 15.87%. You're only above 15.87% of people. And z-score of 1, you're above 84.13% of people. And so that's how it reads. All right, so the tests that make up individual parts of a pre-employment IQ test are designed so that the scores are normally distributed with a mean of 800 and a standard deviation of 200. So this is a different type of IQ test. And a range from 200 to 1400. And we want to interpret this statement. Right, so first, the center of the test is equal to 800. That's your mean. And 3 standard deviations from the center make up your range. So the range is from 200 to 1400, which is a -3 for your z-score, and 1400 is 3 for your z-score. Okay. So 68% of the data will fall from 600 to 1000. 95% of the data will fall from 400 to 1200, and 99.7% of the data will fall from 200 to 1400. Right. That's how this is being distributed for this situation. And all we did with get these numbers is subtract the standard deviation from the mean. 1 standard deviation away, 2 standard deviations away, or 3 standard deviations away. All right, let's look at another example. And so vending machines can be adjusted to reject coins above and below certain weights. The weights of legal U.S. quarters are normally distributed with a mean of 5.67 grams and a standard deviation of 0.07 grams. If the vending machine is adjusted to reject quarters that weigh more than 5.81 or less than 5.53, what percentage of legal quarters will be rejected by the machine? Again, this is based on the ideal amount. So center is 5.67. So we'll subtract the standard deviation as we go, or add the standard deviation. So 1 standard deviation away is 5.6 to 5.74. 2 standard deviations away is 4.9 to 5.81. Right. They are rejecting it based on, oh, I did not do this right, 5.53. I subtracted 0.7, not 0.07. All right, so they are rejecting anything within outside of 2 standard deviations away. Okay, and that's 95% is being allowed. So they are rejecting 5% of coins. Based on and these are the coins that are actually made to be actual money. Some can still get rejected. If they go to and adjust it to 5.46 and 5.88, then they will be accepting 99.7% and only reject 0.3%, which is not many coins. Right. So let's look at some auto prices. A survey finds that the prices paid for a 2-year-old Kia Soul are normally distributed with a mean of 15,500 and a standard deviation of 500. Consider a sample of 20,000 people who bought a 2-year-old Kia Soul. Alright, so how many people paid between 15,000 and 16,000? Well, this is, mean is 15,500. So this is 1 standard deviation away. So 15,000 to 16,000. And so that would be 68% of the people, right, which are 20,000 would be 13,600 people. How many paid less than 15,000? Right, so again, the way this normal distribution is set up, 68% will fall in the middle, and so 32% fall either above or below, but it's symmetrical. So you have 16% above, 16% below. Okay, so 16% of people are below 15,000 or pay less than 15,000, which out of 20,000, that's 3,200. And more than 17,000 is also going to be 16%. Oh, I'm sorry. Hold on a second. That's 17,000, not 15,000. Not 16,000. So 17,000. We have to look at where that falls. So 2 standard deviations away would be 16,500. 3 standard deviations away would be 17,000. So for this one, we're looking at 3 standard deviations away. That's 99.7. So this is going to be 0.15%, which are 20,000. Is going to be 30 people who are paid more than 17,000. All right, in the last section, we'll look at statistical significance, and I'll see you then.